Hello, warriors. This is Miss Lemons, and today I will be walking you through the percent composition of a hydrated salt lab, or the Hydrate Lab. So please have your labs out and ready to go so that you can write in a different color any additional notes that I go over. So let's talk about your objective. You need to determine the ratio of salt to water in a sample of hydrated copper 2 sulfate. But before we talk about how we're going to do that, let's talk about what on earth a hydrated salt actually is. So if you think about what it means to be hydrated, that means to have water. So a hydrated salt is an ionic compound that has water attached to its structure. And ionic compounds, FYI, are also known as salts or anhydrous salts, hence why we call this an hydrated salt. And remember, ionic compounds are a cation plus an anion that have been chemically combined by transferring their electrons in that ionic bond. So each hydrated salt has a unique ratio of salt to water, which brings into mind the law of definite proportions, which compounds combine in fixed and simple whole number ratios. For instance, H2O is a totally different substance from H2O2. In this case, what this chemical formula tells us is that for every 1 formula unit of nickel 2 sulfate, there are 7 molecules of water attached to it to create the hydrated salt, or the hydrate. So when we're talking about the chemical formula of a hydrated salt, we write it a little bit different than what we're used to because we have a covalent compound and an ionic compound kind of sharing a substance together. So the chemical formula has a dot between the ionic compound and the water. And that shows that the two are connected to each other, but are really independent of each other also. And so you can see that here we have our ionic compound, nickel 2 sulfate, and then a dot and 7, the coefficient telling us how many waters there are, and then H2O. So they are not one compound in that they're all mixed together, but they are connected. So we haven't really talked about chemical equations at all, but I'll give you the crash course right now. When you guys are heating your hydrates, what's going to happen is the water will be boiled off in the form of vapor. So we're going to be creating some steam. You might not see it, but we are creating steam when we're boiling off that water. And when we boil off that water, we remove water from the hydrate and we are left with the anhydrate. No water. Or we can also call the anhydrate the ionic compound or the salt or the anhydrous salt. There's a lot of different names for the same substance. So take a look at this equation. On the left-hand side, we have nickel 2 sulfate or hydrated nickel 2 sulfate. And we know that this is one compound because of the dot. And that shows us that these two compounds are still together. They're still sharing the same substance. The S here tells us that we're dealing with solid hydrated nickel 2 sulfate. This arrow here tells us that we are going to go through a chemical reaction, and the heat obviously tells us we are adding heat to make that reaction happen. At the end, we have our products, and in this case, we have 2 products that have been separated by this plus sign. So we start with 1 and we end with 2. We boiled off the water, so it creates water vapor. The G gives us gas. Water vapor is a gas. And we're going to be left within our crucible the nickel 2 sulfate, which is a solid. When you guys are heating your sample for the first time, you are boiling off that water. And when you do that, there will be a color change. Make sure you're taking down those observations of the color change, what you're seeing. And in order to ensure that you've thoroughly heated all or boiled off all of the water, you want to make sure that that color change is pretty uniform across the entire sample. If it's not, it probably needs to be heated a little longer. So remember, your objective of this lab is to determine the ratio of salt to water in a sample of hydrated copper 2 sulfate. And we're going to do this by boiling off the water by using an amount of, and using the amount of anhydrate left over to help us calculate the formula of the hydrated salt. So let's go over a few safety reminders. And in the slides to come, you'll see steps in parentheses. So you should look at your procedure section right now and get ready to add or highlight or emphasize any of those steps that I'm going to be talking about now. So you do have an image of the general lab setup. It's important that you make sure everything is in their place. Get your ducks in a row before you start the lab, and make sure your setup looks just like this. It is one of the most complicated lab setups that we'll have this year, so make sure it looks the same as the image. We are going to be using a new tool today. It's called the crucible, and then also the clay triangle. I want you to notice that the crucible is just kind of nested inside that clay triangle. These are both really, the crucibles are very fragile. If you find a crack in your crucible before you start, please make sure you give your crucible to your teacher so they can replace it. You see, they're very fragile, and if you have a crack and you heat it with a crack, you will probably shatter your crucible. Also, if you move crucibles that have been heated or superheated from hot to cold too rapidly, they will go through thermal shock and they will shatter. So let's avoid that by being patient and allowing them to cool. When you heat your crucible or the sample inside the crucible, you want to make sure that the bottom of the crucible is touching the cooler part or the top portion of the light blue cone on your Bunsen burner flame. You don't want to avoid you want to avoid heating that hydrate too quickly because it will start to bubble and splatter, and you could potentially lose some of that anhydrate outside of the crucible, which would skew your calculations later on and make your masses lighter than they actually are. Not good. So heat it low and slow. When you're cooling your crucible, you need to make sure you allow it to cool for at least 5 minutes. 5 to 6 is what's suggested. And you need to do this before you mass it because the temperature or the mass will fluctuate if it's too hot. Plus, you could put your crucible into thermal shock if you set it onto a cold plate, onto a cold balance. When you are waiting for your crucible to cool, do not turn off your Bunsen burner flame. This is going to save you a lot of time, and time is of the essence for this lab. So just move your Bunsen burner to the side and keep an eye on it. When you're done cooling, it should be cool enough for you to touch, 5 to 6 minutes, but it will be warm, but not hot. Speaking of moving that crucible, even if you can move it with your hands, don't. Just use the crucible tongs that have been provided for you. Please make sure you're using your tongs like the image on the right and not like the image in the bottom left. If you nestle the crucible in the little niche or the little nook of your crucible tongs, you will probably drop it. And honestly, this is the way that most students accidentally shatter their crucible. Not a good idea, especially when you have your sample in there. You're going to have to start the whole lab over again. So let's avoid that by using our crucible tongs correctly. When you are looking at your table, this is right after the procedure, there are no units labeled. So take a moment right now to consider what units you're going to be using to measure the information in that table or the data in that table. Add them now. Also, don't forget to add qualitative observations to the right of that data table. I want to see some detailed, high quality, qualitative observations of what you are seeing, hearing, and perceiving the whole time while you're heating that sample and cooling it. So the last note I want to leave you with is you really need to make sure you are taking advantage of the time that you have in class. While you're waiting for your sample to cool, you should be actively working on questions in the PostLab, calculations in the PostLab, or at least putting the skeleton setups for them, checking over your observations and trading observations with your partner, checking your units in the data table. There are so many other things that you can be working on while this is cooling. And then finally, I'm actually not going to be spending time in this video talking about the calculations of the Hydrate Lab. But if you feel a little bit uncomfortable with those calculations and you need a little bit additional support, I will be providing a video walking through an example set of calculations that are identical or very close to identical to the pre-lab that you have on yours, on your own lab. So feel free to take a look at that video, and that's all I have for you today.